Ulf Danielsson, can you summarize this year's Nobel Prize in Physics, please?
Yeah, it consists of two parts. There is one part which goes to Roger Penrose for the theoretical understanding or even prediction of the existence of black holes. I mean, the history of black holes go way back in time to the end of the 18th century. And then, of course, through Einstein's general relativity, we had the tools to actually start to describe these objects for real. But since the mathematics is so complicated, it took several decades before one really was able to understand what's going on. Could such objects actually form in the real world? And that is what Roger Penrose did. He understood the mathematics, he introduced new tools, and then could actually prove that this is a process which you naturally can expect to happen, that a star or something else collapses and turns into a black hole. Before Penrose, that was far from clear. Many thought that such objects were only mathematical artifacts that couldn't form in the real world. So Roger Penrose, he laid a foundation, the theoretical foundation, so we could say that yes, these objects exist, we can expect to find them if we go out and look for them. And this was sort of a journey that started in the mid-60s. And what Rainer Genzel and Andrea Ghez have done is to prove really that such objects exist. And they found one, a supermassive black hole in the center of our Milky Way. And the way they did that was that they monitored stars which were orbiting around something that they couldn't really see. And that, of course, required very sophisticated equipment to be able to do this and make these observations. So it took several years. And then this work has continued, and one has been able to look further and further in and closer to the black hole to start to test general relativity.
So what is a black hole?
Well, so far, I mean, what the current understanding of a black hole is that it's sort of a region in space where gravity is so strong that not even light can leave it. I mean, if you think about the Earth, on the surface of the Earth, we have what's called an escape velocity, which is equal to 11 kilometers per second. That means that if something is directed upwards with that speed, then it will leave the gravitational field of the Earth and never come back again. Now, a black hole, that's sort of an object, you would say, where the escape velocity is like the speed of light. Now, in fact, what turns the structure of a black hole in general relativity turns out to be very much related to the structure of space and time. So it's like a region in space and time which is so warped and curved that it's impossible to find your way out again. In fact, what happens is that when you reach the boundary, the horizon of the black hole, time, I mean, we always carried on by time. You cannot compete with time. I mean, there's no way to stop time or go back in time. But the point is that when you go inside of the horizon, the direction of time is pointing inwards towards the center of the black hole, where it actually ends, because in the middle, that's sort of where the direction inwards ends. And that means that the way that you're caught by the black hole, it's as powerful as the flow of time itself. So it's as difficult to get out of a black hole as moving backwards in time. That's our current understanding of a black hole. That is what general relativity predicts. And everything that we have seen so far is compatible with that picture. Still, and that is of course why one continues to do all these observations and measurements, is that it could be that there is something else, something different that you will be able to discover when you move really close into the horizon. So we cannot say for sure what's going on. But we know that these objects exist, but we are not quite sure about their real properties. There could be new physics. There could be surprises.
There have been a lot of black holes in science fiction, actually, and there the end of time is also a beginning of something else inside the black hole. You cut the time and go or travel out in another time, past time, for example. Would that be possible, you think?
It's not very likely, actually. I mean, the most likely possibility is, in fact, that it's a one-way. It's a one-way road, and there is no escape. There's no way to come out somewhere else. Of course, I mean, who knows? But according to the current theories, our current understanding, if once you're into a black hole, I mean, that's the end of it, basically. Well, who knows? I mean, it certainly marks the bounded limits of our knowledge, and you can start to speculate in various ways. But a good guess is that once inside the black hole, there is no way out.
Just the end. But you mentioned that there are black holes actually out in the space. So where are they?
Well, there are probably lots of black holes. The one which is awarded this year's prize, the discovery of the black hole at the center of our Milky Way. But probably there are many similar examples all through the universe, or every galaxy is probably hosting a big black hole in its center, many which are much larger than the one in our Milky Way. And then furthermore, we expect there to be lots of smaller black holes sprinkled across the Milky Way, which are the products of a supernova. I mean, stars which have run out of fuel and exploded, and then giving rise to these black holes. So black holes are all over the place.
So how dangerous are they if we come close?
Well, not especially dangerous at all, really, because the likelihood for us to encounter a black hole is really very small. It might very well be that there are black holes among the stars, black holes that we cannot see. But I mean, remember, I mean, it's very rare that you would collide with another star, right? Another star would collide with our solar system. That doesn't really happen, and there is no difference with stellar mass black holes which are moving around in the Milky Way. They will not just come and hit us. The probability for that to happen is very, very small.
But what would happen if you come close to a supermassive black hole?
Okay. Now let's say that you were able to travel on purpose and wanted to examine such a black hole. Then it's actually the bigger it is. Because if it's a really big black hole, like the one in the center of the Milky Way, then you can, without really getting hurt in any way, you can travel all the way towards the horizon and even cross the horizon and enter into the black hole without being stretched by gravity. If the black hole is small, like the ones with just a few solar masses, then you cannot even get close before gravity will pull you apart. If you jump in with the feet first, then gravity will be stronger in your feet than in your head, and you will be just torn apart. But for a big black hole, you could actually imagine such a journey into it. Then, of course, it's a dangerous place still, because there might be lots of other stuff happening. I mean, there might be hot gases and plasma, which is swirling around the black hole, and dangerous radiation. But as far as gravity is concerned, a big black hole is not really that dangerous. Of course, I mean, once in, you cannot get out again, but otherwise it's okay.
Yeah, it's just the end.
It's just the end, otherwise it's fine.
Reinhard Genzel and Andrea Ghez came actually quite close by observations.
They did, yes.
Did they expect this prize?
Sorry,
Did they expect the Nobel Prize?
I have no idea.
What did they say when
they were very, very happy, obviously, clearly, and that was a very pleasant experience. I mean, to share that moment with them.
Thank you very much, Ulf Danielsson.